Okay, so let's talk about what we would do each day. This morning in one of my algebra ones, I was pleasantly surprised because I went to their week one and I went to their homework help, and yours is period 4, and I did have some problems waiting for me. Here in this case, that doesn't appear to be the case. So it can't be that we don't know how to take a screenshot, because not one person has asked me how to take a screenshot of the device. If you did, I'd be willing to help you. I'm familiar with almost any device you can think of that you're using, and I can help you take a screenshot and show you how to post it. Maybe it's just that you understand it all. That would be fine also, but hopefully once these due dates come and go, we don't say that we didn't understand it or anything. This is also available to you. And it was real nice. They posted it, I copied it, I pasted it on the software, went over it step by step. It worked out really nice. So then other than that, now we can get started on the notes. Now we do have some new notes today, but since we have quite a bit of time to do what are known as transformations. We have really like the next 4 classes. So even if like really we're scheduled to do 1 transformation each day, but there's a little bit of wiggle room. So I do want to go back and do the last part of the intro to geometry. Oh, I hate this program. You see how it just crashes?
Yeah, like. So you didn't minimize it? It just
crashed. It's been doing that. I even uninstalled everything and reinstalled it. It's just completely ran.
This is the software that goes
with a Promethean, yes. And it just decides when it wants to do that. Okay. So this is where we left off on the last page. This is the last page that was available to you. No?
Yes, zoom in.
And it's even so hard to do that. It's like, it's tricky with the mouse. Okay, so it looks like on this page, all they really wanted to do was like a sketch. Okay, so a protractor. I'm not gonna do a sketch of a protractor. Do you guys know what a protractor looks like? It's used to measure angle. One of the Khan Academy lessons gives you practice with how to use these. You won't be able to see this on the video because I'm holding it in my hand, but the way a protractor works is either somewhere here in the middle, or in this case, it looks like it would be this little indentation here. What would go there? Which point? The vertex, good, yeah, the vertex. Okay, and then one of the sides of the angle would have to go along the 0 degree, and then wherever the other side goes, that's how many degrees your angle is. This thing just died on me?
Yeah, everything got it.
Everything that is not today. No, it's connected. It'll just beep for some reason. Okay, an acute angle. So let's just do a sketch of an acute angle. What do we know about an acute angle? It measures less than 90 degrees. So there's an acute angle. What could I name that acute angle? I can call it BAC, or I can call it CAB, as long as you have the angle symbol, which coincidentally the angle symbol kind of looks like an acute angle. That's the symbol for angle. How about a right angle?
90 degrees.
Yeah, 90 degrees. Just to save time, I'm not going to write the points, but I'll just quickly sketch. Right angle. On a obtuse angle?
Bigger than 90.
Yeah, in between 90 and 180. I would want to normally label, because this technically is asking for a labeled sketch, but I think we had enough of these on the last notes where I could skip that and you can go back and look at them. But I would want to put 3 points there at least, you know, one on each side and then one on the vertex. What was a straight angle?
Goes off one direction.
180 degrees. What does it look like? A straight line. And now this is something I know that we said. Let's see who has a good memory, who pays attention. What was another name I gave you for a straight angle? Supplementary is when two angles add up to a straight angle. But then I told you that there was some other phrase that can be used. It's 2 words. What's another word that can be used for nobody remembers? Nah. Didn't write it, just said it. And it took a while for us to come up with it also. Opposite rays. If you see opposite rays, that's just a straight angle. Opposite rays. Complementary angles. What do we know about complementary angles? 2 angles, yeah, pair. It has to be a pair of angles. Do they have to be adjacent? Do they have to be like share a common vertex? No, they don't have to. They can, but they don't have to. They don't have to have a common vertex. So, yeah, the most common sketch, though, or the easiest way to sketch it is if they did share a common vertex, and then you would do something like that. Those two, I haven't labeled it. I'm just trying to save some time so I can get the translations. But those 2 angles that I drew there, those angles would be complementary. How about supplementary? 2 angles, a pair, yes, that add up to 180. Do supplementary angles have to have a common vertex? No, they can. They don't have to. If they do, what else can you call supplementary angles that share a common vertex? Close. It does have the word pair in it. What? Linear pair. A linear pair, yeah. Like here, what I'm going to draw for you actually is a linear pair. Just happens to be that those 2 angles that I just drew are supplementary. These we haven't gone over. And actually, this is part of the next unit.
Yeah.
So I should probably skip that. Yeah, corresponding angles is part of the next unit. Corresponding sides. I don't even know where we go over that in geometry.
Yeah.
I've never even seen that in geometry, corresponding sides. A bisector, okay. We talked about bisectors. What 2 types of bisectors did we talk about? Say it again.
I heard it. Y'all said
You
it.
said it?
Angle.
Yeah, and what's your name? You're doing good today. You're answering a lot of questions. What's your name? Josh. Okay. Yeah, definitely an angle bisector. Sure. That's a ray that cuts an angle in half. And then you would see those marks. What other type of bisector did we go over?
The P word.
Point.
What type of point? A midpoint, yeah.
I was thinking perpendicular bisector. Did we talk about that yesterday?
We've talked about perpendicular, we've talked about bisectors, but those are special segments. That's like when we get into triangles. How are we feeling there, man? Are you bummed out because it's Friday? Is it Gabriel? Is that his name? What's his? Joseph. Hey. It's alright, don't worry, man. Monday's around the corner, dude. Like, you don't have to be that bummed out. Yeah, it happens. Yeah, the other type of bisector would be a segment bisector. What cuts a line segment in half? As we said, a midpoint. Circle we haven't really talked about, but okay, let me just know what the definition of a circle is. All if I draw a point and I wanted to know every single point that was equidistant, what does that sound like? Equidistant? What does it sound like? Okay, equal what? Equal distance. If I wanted to find out everything that was of equal distance, I would draw a circle. All the points on that circle, I know it's hand drawn, but every point on that circle is the same distance from the point I drew in the middle. Congruent. What does congruent mean? Equal. Yeah, equal. What are some of the symbols for congruent? If we have congruent segments, we'll put a little slash through them. If we have congruent angles, you can either put matching arcs, like either single arcs or double arcs, or you can put an arc with a slash through it. Okay. Postulates, theorems, we'll worry about that later. Yeah, the main difference between postulate, it's more of a technicality. Think of both of these as rules, but it has to do with the technicality is if it's been proven or not. Okay, a postulate has not been proven, but a theorem has. We assume that postulates are true. Theorems, we know them to be true. Any questions there before we move on then to transformations?
Lots of vocabulary in geometry.
And that actually might be part of your reason for either liking geometry more than algebra, or for some kids they don't like it more than, because out of all the different disciplines in math, I would say geometry is the least mathy, if that makes any sense. There's more of a memorization that plays a part. So it kind of mimics more of your like a history class or an English class where you don't have to be that great at adding, subtracting, multiplying, and dividing. But you can kind of get by because it's a lot of just studying and memorization. So that could be a good thing, that could be a bad thing. So. Alrighty. Today's main lesson is on translations. That's what the focus of today's lesson is a translation. A translation is a type of transformation. So sequentially, since I'm going over this first, that's when I'm going to give you an introduction into transformation. So like today's lesson will have a little bit more than the next three will have. But the way it's paced out on the calendar is we have 1 day set aside for each transformation. Okay. So what is a transformation? It's a function that changes the position, the shape, and or size of a figure. When we talk about figures, we can talk about shapes, lines, segments, anything that we talked about before, which regardless, what are all of those made up of? I'm talking about a line segment, an angle, some type of a shape, a polygon. What are all those made up of? Points. Yeah, they're made up of a collection of points. So when you get a point, and transform it, change it, okay? The original point is known as the pre-image, and wherever it ends up, wherever that point ends up, is referred to as the image. If my pre-image, if my point is point A, not every point is called point A, it's whatever happens to be called, it's B, C, whatever it's going to be called. But if there was a point A, and point A were to change its position, its location, a point is a location, if you change that location, wherever it comes to rest, wherever the image is, would be referred to as A prime. It's called prime notation, a little apostrophe, A prime. If you have a point B and it changes, then you call it B prime, C, C prime, so on and so forth. So what I've called before coordinate notation. I was looking at the notes. They called it here arrow notation. I saw it called arrow notation, but okay, fine, we'll call it arrow notation. I know of arrow notation more in algebra when you start doing limits. We study limits and arrow notation, but here in this, since all our assessments are standardized, I want to make sure you know the terminology. So, but for coordinate notation, we call it arrow notation. If a point is a location, and a location on a coordinate plane is x comma y, the rule is the transformation that it undergoes. Which transformation are we going to learn about today? Which transformation?
Sounds a lot like transformation.
It does sound like transformation, but it's translation. Yeah, we're going to learn about translations. Jamal's going to learn what he loves. That's his favorite. Transformation is a translation. Is he sleeping or dabbing? He's doing both at the same time. Multi-talented. Then after it undergoes this transformation, then A prime, wherever it comes to rest, would be some result of the original location, and then in blue, you have the transformations that it undergoes. Mathematically, those transformations can occur by what type of operations? When you, like for instance, today we're going to do translations. Translations is where the adding comes in, so I just gave you one of the answers. What could you potentially do to transform something? You can add. That's one of them. What's the other operation you see there? Multiplication. But wait, Mr. Romero, what does that mean? I mean, you can't divide? Well, yeah, you can divide, but those are inverse operations. Dividing is the same as multiplying by a reciprocal, so it can be expressed as multiplication. Oh, but how about subtracting? Does that mean you can't subtract? Yeah, sure you can. What is subtracting the same as?
Adding.
Adding a what?
Negative.
Adding a negative. Yep, adding a negative. So today's the easy one. If you want to call it that, translations are the ones that are basically simple. So let's see if I can zoom in on this too. All right, I'm getting better at this now. So here's an overview of what's to come. Can you tell by my graphic there how many transformations there are going to be? Well, I guess I also said it earlier. Jamal knows. Jamal, how many transformations are we going to study? Yeah, it's a tough one. Skylar? Four, yeah, 4. I said there's going to be the next 4 days. There's 4 of them. And you can tell by looking up here, what are those 4 going to be called? Translation, that's today. I don't know if I have them in the right order. I don't know, I'm not sure if the order is right, but so we can just read them there. Reflections, rotations, and dilations. Underneath each one, remember we talked about what operation you could do to the pre-image to get the image? These would be the operations. When you are translating, what are you doing to the pre-image? You're either adding or subtracting. If a point is getting reflected, it has to do in some way, shape, or form with multiplying by a negative number. Okay? Rotations can occur by also multiplying by a negative number. We'll get more specific. We have a day that's dedicated to each one. This is just an overview. And then finally, dilations have to do with just multiplying and dividing. There's also some lay terms. You know what the word lay means? Can you say like the lay person? Lay? Kind of means like common. There's some more common words that can be used to describe these. So if I am translating, that might sound like a fancy word, but you know what translating is synonymous with? What other word can I use to describe translate? I would think maybe they've heard these before.
We don't do these transformations.
Like normally when I teach geometry, the kids will they'll at least know the names of them, but Okay, a translation is also referred to as a slide. You know, a more common word that can be used for translation, so that sound I hear is you guys writing this down. If you ever, sometimes I mix and match these words without even thinking. So if you ever hear me say slide, we're sliding, we're translating.
Just taking an image and sliding it.
Okay. Come on, here. How about reflection? Here, maybe we can use some context, you know, and we can just use just regular the English language. If I were to say reflect, what do you think a more common word for reflecting is? When you look at your reflection in the mirror, what does it appear that has happened to the image? Flip. That's exactly right. It's a flip. Yeah. When if you hear me say flip, we're reflecting.
Definitely write these down. Slide, flip.
Mm-hmm. How about a rotation? If something is rotating, what would be a more common word for rotation? Turn. Turn. Yeah. Turn. And how about dilation? Okay, so what happens when your eyes get dilated? They do get bigger, and after they finish getting dilated, what happens to your eyes? Yeah, so you can say shrink or expand. An expansion, shrink, enlarging, reducing. In algebra, the algebra words, I think I don't know if here they do an algebra one. Do they do do they teach transformations here in algebra one?
I don't think so. Right?
Like how to transform functions? No. So in algebra for dilation, they use the word stretch and compress. If you hear stretch and compress, that also means dilate. Okay? Now these can get categorized. The first three that we went over are referred to as the rigid motions. We'll talk about what that means now. The last one, dilation, that's the only non-rigid motion. Three of these are rigid, one of them is non-rigid. What does it mean to be rigid? We'll go over each one, but the easiest thing is if you're rigid, it doesn't change size or shape. Size stays the same, shape stays the same. Position might change, but size and shape remain. Whatever it started looking like, it's going to look the same way.
For example, like a reflection, if you're looking in the mirror this morning, does something change when you're looking in that mirror? Is there a change?
Yeah, unless you're like in one of those mirrors in the gym where you look all swollen and stuff, you know, if you're looking in the mirror, you're still gonna see yourself. You might be flipped, but it's not like I look in the mirror and then I see Brad Pitt. It doesn't work that way, you know. I know, that's why I said I don't. But, so technically though, properties of rigid motions. Rigid motions preserve distance. Meaning all points, whatever points move, they're going to move the same. All the points are going to move the same. They preserve angle measure. Any angles that are in the shape stay the same. They preserve betweenness. So relative to each other, whatever points you're looking at are going to stay the same distance from each other relative. Collinearity. Any points that are on the same line will remain on the same line. And then parallelism. If any lines are parallel, they'll remain parallel. Might not be going in the same direction as they were at the beginning, but they're going to remain parallel. Okay, then non-rigid motion. What's the only non-rigid motion? What is the only non-rigid motion? Who's paying attention today? Easiest question to ask.
What is it?
Dilation. Okay, so yeah, the quicker you answer, the quicker we get through this. So sometimes I'll ask choral, what are called. They're normally frowned upon, but in order to get through a lesson, I'll ask choral questions, meaning I'll ask them to anybody who wants to answer. You just shout it back out so we can keep on moving. If I need your attention, then I'll call you out, like Harley and stuff, and I'll say, hey Harley, non-rigid motions, right? What's the big thing with non-rigid motion? With the dilation, now we're allowed to change size and shape. When you stretch or compress an object, it could change in size or shape. It is the opposite of what you see here. Well, actually, you know what? I take that back. And not everything is the opposite. Non-rigid motions will still preserve angle measure, so the angles will stay the same. We still have betweenness, collinearity, orientation. Everything is the same except for that the size, and where that is shown here. when you have a scale factor, what that's saying is that the size can change. The size and the shape can change. We'll worry about the others. I already have the notes posted for the month, and I want to say that since dilation is the only non-rigid motion, you're going to see all this stuff again on dilation, and we'll go over it again. Since today we're working on translations, we want to focus on the rigid motions. Any questions on this slide? But wait, mister, I didn't have enough time to write all that down. Where can you find these? Yeah. See if I can do this right here. Oh, there it is. All right, getting better, getting better. So now we'll get into just translations. So it is convenient to describe translation using vectors. Can you use context clues here to read through that first paragraph and tell me what a vector is? Just read through it. See if you can tell me what a vector is. If you can paraphrase. Yeah, Jamal. A vector. Here they talk about vectors and then they give you an example. What they've done in this graphic is they have mapped a pre-image into an image. They're showing it using vectors. Okay, get in there. It's an arrow. It's an arrow. It's a vector, it's an arrow. Okay, they're shown using vectors. Oh well, I see. I haven't taken a physics class in a while, but I want to say the physics definition of a vector is a direction and a magnitude. I might be wrong on that, but if you have a direction and a distance, then that's what a vector is. A physics word. And let's see who's listening. What did I tell you we are actually going to be doing when we translate? Oh, well, yes, fine, sliding is another way of saying it, but mathematically, what are we going to be doing? When we translate, what type of math are we going to be doing? Adding and subtracting. And as you can see down here, you can read through this on your own, but this tells you if I'm going to translate, if I translate, having a bad day today. Oh, I put it on the wrong one. It's over here. Okay, so translation to the right, adding. What variable is getting added when you're going to the right? What am I adding to? If we start off with an x and a y, which one is getting added to there? The x, yeah. If you want to go to the right, add to the x. When I translate left, what am I doing? Subtracting. What am I going to subtract from? Yeah. No, it's still the x when I want to go left. Translate up. I'm adding. What am I adding to? The y. When I translate down, I'm going to subtract and subtract from the y. Okay, so I've already given myself my 10-minute warning, so let's see if we get to some examples. I think I have examples. Perfect. Examples are coming up. Okay, so here we have some coordinate notation, or what they call arrow notation, given this point. This point here is my pre-image, and I want to follow this rule. Okay, this is the rule that I want to follow. How would I apply that translation? I would use coordinate notation and say, okay, what's the x of my pre-image? What is the x of my pre-image? At what x am I starting at? 4. Then my rule tells me to get that x and add 2 to it. Comma. What is the y of my pre-image?
-2.
-2. What is my rule telling me to do to my y? -8. So therefore, then my image in prime notation, we started off being called p. This will be p prime. Would be 6, comma, -10. Sorry for the handwriting. That's a -10. These Prometheans compared to the smartboards, they're so sensitive when you lift the pen off that it like, even though the pen is not touching,
Yeah, I've used a smartboard in the past, not a Promethean.
I think everything considered, that's the one I prefer. Any questions there? The coordinate plane shows a translation of 1 unit to the right and 6 units up. Okay, this is not an example. This is just showing you already. This is another type of notation called displacement notation.
And I will say, I know Coach Bowles was saying that in the past, it's good for them to see it, but I don't think we're putting those on displacement notation. We're not going to put them on tests and quizzes.
Okay.
Standardized tests, you guys might see, like a district or state test, you might see displacement notation.
You know, so all this displacement notation is saying, where did you move to the right / left, and then the second number tells you where you moved up or down. If it's positive, it was either right or up. If it was negative, you move left or down. So here's the pre-image. This, you can tell every single point with all of these have in common. This is one of the neat things with technology I should be able to do. What I have there is I mapped a motion of going 1 to the right and 6 up. You can see that all of these went 1 to the right and then 6 up. You see a +1 and a +6. All the same thing. Charles, you okay? Mm-hmm. Thinking? Okay. Okay, give the arrow notation and the displacement notation of the transfer. All right, so let's just stick to arrow notation then. So as not to confuse you, let's just stick to arrow notation. Let's describe what happens here. This is color coded for you. I have seen the quiz that you're going to take, and I can tell you that it's going to look in this format. It's color coded for you, black and blue. So which one here is the pre-image, the black one or the blue one? Good. Okay, and not because of the color, because of the notation. Remember, prime notation, that's the image. So when you see the little apostrophe, is that what it's? The apostrophe, that's prime notation. So let's, in arrow notation, let's describe what occurred. We got our original x's, and then did what? Where are the new x's compared to the original x's? Where is the blue? Where are the blue points compared to the black points with respect to left or right? That's what that goes with left or right. 1 to the right, so I will put +1. 1 unit to the right. Okay. Where are, and actually, you know what? This is bad. I'm being silly here. Let's make it look correct. Sorry, this should say x, comma, y. Then I should see an arrow, and then I'll write +1. Okay. And then the y's, what did the y's do? Yeah, and then nothing happened. So let's leave it as a y.
So this just shifted 1 to the right.
Mm-hmm. We did a translation 1 unit to the right. If you were asked, there are some problems on the quiz that ask you to verbally describe what occurred. So if you were being asked to verbally describe this, you would write down as a narrative, a sentence, translation 1 unit to the right. Translation is the transformation. Where did it go 1 unit to the right? Okay, given this pre-image and translation on the right, determine the coordinates of the image. So here in arrow notation or in coordinate notation, whichever you prefer to call it, we have our rule. This is the rule that we're going to follow. I would draw it first, just to make sure you don't make any mistakes counting. I would try to draw it, and then we'll write the new points. That's what they want us to do here, right? Mm-hmm. Determine the coordinates. Okay. So what is this rule telling us to do? To translate where? Give me a direction and give me a magnitude.
Left 4 and up 2.
Very good. Left 4 and up 2, so we get all these points and count. 1, 2, 3, 4 left, up 2. That's gonna be R. From S, 1, 2, 3, 4, up 2. This will be S. From Q, 1, 2, 3, 4, up 2. T, 1, 2, 3, 4, up 2. So this is Q. This is T here. And actually, I should be calling it prime. S prime, prime, prime.
Sometimes it'll ask you, like, there'll be questions like that last one where it says, you have to look at the two images and decide which one went. So make sure you look at the one, the pre-image going to the image, because I know a lot of times students look at the image and they go the opposite way. So just be real careful about the prime versus.
Where is Q prime located? Where is that location? Where's Q prime? Negative 4, negative 1. Yeah, where is R prime?
Negative 3, positive 4.
Good, negative 3, positive 4. Where is S prime? 0, 3. And where is T prime?
Is T prime the diagonals to the
Yeah, sorry, I kind of drew it away, but it's this one here.
negative 1,
Negative 1.
negative 2.
All right, so that's where we'll stop. The good news is that because we do have a little bit of time coming up in the next 3 classes, I will finish this on Monday before we move into the next transformation. The bad news is that I believe translations fall under the week 1 assignment, which is due Sunday. But I think I've given you enough to get by on that assignment. Part of the reason why I have so many of these is because the Khan Academy was a little too easy, I think, in my opinion, but you should be able to get by.